Okay, let's look at this question here. We have two resistors made up of some materials, for example like carbon. They are made of the same material and they are of equal length, but one has twice the diameter, as you see here. Which one is going to have the higher resistance, R1 or R2? R1 would be the resistance of this first one and R2 for the second one. Now, remember R rho, same material, so it's the same rho, L over A. We increase A, we decrease the resistance. L is the length. So I have more area here, meaning less resistance. So 2 is going to be less resistance, so R1 is larger than R2. I would like to note here as well, it's not a linear dependence, because the area is equal to the radius pi r squared. I'm writing a small r here. Now for the first one, pi times d over 2 squared. That's A1 for 1. For the second one, A2 is going to be equal to pi R2, but R2 is going to be d squared. You notice here I have 1/2 squared in the denominator, which makes it 4 times. So actually the resistance is 4 times. R1 is actually equal to 4 times R2. Okay, let's see. We have another question here. Compare the current through R1 with I2, the current through R2. And we have a big difference between R2 and R1. The thing here, we have only one path for the charges to move through, so the current has to be the same. Both resistors are in series. Compare the voltage across R1 with the voltage across R2, which is 10 times R1. The currents are the same, however, VR1 is equal to R1 times I. VR2 is equal to R2 times I. We called it R10 here, which means VR2 or VR10 or V10, like they called it here, it is 10 times R1 times I, which makes it 10 times V1. So that's our answer. That looks like the same question. Okay. So here we have a circuit, we have a battery, 2 resistors, but then we have an open switch, so the circuit is initially not complete. And the question is, what happens to the current through R2 when the switch is closed? What I would like you to pay attention here is the voltage across R2. Right now, with the switch is open, when the switch is open, all that red line is at the same voltage. Now, I'm going to make it green for the other side. All of this is also at the same voltage. The interesting thing here, since we don't have a current through R3, all of this is at the same voltage, which is the low voltage of the battery. And the voltage across R2 is just the difference between the voltage at the red end and the voltage at the green end, which is the same as the voltage drop across the battery. It is in parallel with the battery. So the current through R2, we can find it using Ohm's law. V across R2 is equal to R2 times I2. I'm labeling it as I2. So I2 is equal to VR2 over R2, and we said VR2 is just the same as the voltage across the battery. Okay. Now, what if we connect the switch? Now, if we connect the switch, this is going to be closed, meaning the voltage here is going to be the same. Now the resistor is going to be active. It's going to conduct current. So it's going to drop the voltage from the green in the other side to the red. The voltage drop across R3 is going to still be E, the same as the voltage drop across the battery from red to green. However, also what you should notice, the voltage across R2, the voltage drop across R2 is still from red to green. It didn't change. So we should have the same current through R2. That's what the question is asking. And that's a good thing, because in a house, when you turn on another switch, you don't like the light to dim in a particular room. Of course, you know that in reality, it's not always the case. And it's not always the case because actually these wires are not ideal wires, and they have resistance as well. Because they have resistance, the voltage across R2 is not going to be equal to E, and it's going to depend on the current in that branch. Okay? But that's not what this question was asking. Ideally, in an ideal case, what's going to happen? The current should remain the same. Okay, going back to the same problem, what happens to the current through the battery when we close the switch? Okay, and that's a good question. Initially, when the switch is open, the battery was feeding just R2. And we had a current through R2 that we called it E over R2. But then when the switch is closed, we are going to have a current through R3 as well. Let's call it I3. And that's going to be E over R3. So I have two currents. Where are they going to come from? From the battery. If I call this I is going to be divided up into I2 and I3. When I3 is 0, I2 is equal to I. But then when I3 is not 0, I is going to be larger than I2. So it's going to increase. And obviously, that makes sense. If I have more light bulbs turned on, I'm going to use up more electricity. I'm going to use up more energy. I'm going to require more power from my power source, my battery. Okay, so here we have a question. We have Mr. Sahu that uses a power strip to plug in his microwave, coffee pot, space heater, toaster, guitar amplifier, all in one outlet. This is dangerous because of what? Okay, remembering that power strips are powered in parallel. This is dangerous because each of the devices is going to require a certain current. And the wires here is not really ideal. It's going to have a resistance. Because it's going to have a resistance, power in that wire is equal to Ri squared. R being the resistance of that wire. Now, as we add appliances, the current here is the sum of all currents. The more appliances, the larger this current is going to get. Look at the power. It's I squared dependence. The larger the current, the more power dissipated. Meaning, the hotter the wire is going to get, so it becomes dangerous where it can create a fire. So this is the answer. The current in the kitchen circuit is too high, making this as a fire hazard. Okay, in this question we're comparing three configurations The first one, we have one resistor, and then two resistors in series and two resistors in parallel. The resistance for one resistor is R, two resistors in series R plus R, so twice R. Two resistors in parallel, 1 over R equivalent is equal to 1 over R plus 1 over R. So R equivalent is just R over 2. So the smallest resistance is in C. Okay. Now, where should we add bulb C in order to get A to shine more? So to get A to shine more, we need the current here to increase. Remember a few questions back. How did we have the current increase? By adding a resistor in parallel to this resistor. That's the way we got this current I to increase. So same idea here. We want the current in A to increase. So what we need to do is put a light bulb in parallel with B. So by putting a light bulb in parallel with B, I'm decreasing the resistance here. I'm decreasing the overall resistance seen by the battery. So I'm going to have a larger current through A. Okay, again, to explain that. Now, initially, the battery sees the resistance of A and B. So it sees twice R. Now, when I put a resistance in parallel with B, the resistance RBC is going to be half of R, because resistors in parallel provide a lower resistance, and if they are the same, it's going to be just half. So the overall resistance seen by the battery is going to be R for A plus R over 2. So it is less than this twice R. Again, V is equal to Ri, that's Ohm's law. If I have a smaller R for the same voltage of the battery, I'm going to have a larger I. Larger I, meaning the light bulb is going to be brighter. So this is the way I should install C. Okay. In here, we would like to predict the relative brightness of the bulbs. Okay. Now notice here, this one is going to have the same current as the battery. However, that current is going to be divided in two here. So F is obviously brighter than A and B. That same current through the battery is going to be divided in 3 here. Which means F is the brightest, A and B are the same brightness, but they are less bright than F. So we have F larger than A, which is equal to B. And this is larger than C, since it's a third of the current through F, not half, so it's going to be larger than C, which is equal to D, which is equal to E, since they are same light bulbs. Okay, the last question here for this exercise. Resistors R1 and R2, are they in parallel, in series, or neither? Okay, in series means I have to find sorry, let me take that back. For R1 and R2 in series, every loop that I draw in the circuit should include both R1 and R2. Okay, let's start with one loop here. Perfect, it has both of them. Okay, now let's start another loop. This one has R1 and not R2, so they are not in series. Okay, so not in series. Second test for the parallel test. I need to find a loop in the circuit that has only R1 and R2 and nothing else. So this loop has R1 and R2 but E2 as well. So that does not work. This loop does not have R1 and R2. So that does not work. This loop does not have R1 and R2. So that does not work. So all possible loops that I can draw in the circuit, none of them includes just R1 and R2. So they are not in parallel. So my answer is neither.